right. Thanks a lot for joining me today because I have been talking to myself for the last 9 minutes um, because I didn't realize that YouTube was not going to be, go online. I thought I was online, so I was talking to myself for the last 9 minutes. But it's okay. Now I have realized that the stream has not started, so I have just started. Sorry for making you wait for 10 minutes. I hope to resolve. We hope to resolve those technical issues on the next episodes of the DevLog. So everyone, welcome to the second episode of the Omchain DevLog. Today we'll be talking about the blockchain technology and how it actually works, how we can be, benefiting from that technology. It's important for us to understand how blockchain technology works because without understanding the technology, we cannot actually deliver products that are, feasible and that are usable in real life. Previously, we have mentioned that we're not planning on expanding our operations on DeFi field because most of the DeFi products, not all of them, but most of them are focusing on issuing synthetic tokens, synthetic dollars, which causes great money issuance, which makes the coin prices go up, but then ends up with cryptic asset prices going down and a market crash, we could say. So now today we'll be focusing on how blockchains actually work. Like people are talking about blockchain technology all the time, but like what's it about? Like what is the blockchain technology about? How does it work and how we can utilize in our real life? This week we were talking about a business partner about you know this technology and what it can prove to humanity. And they realized that as I was speaking, sorry for that. As I was speaking, they realized that it's actually something the end user or the citizens of a country or like the consumers of a product should be asking or like demanding the blockchain technology from the company or like the government or the service provider that they are receiving service from. So it's important for us to understand this technology and understand the vision behind it so that we can understand how everything works and why we actually need it. So let's just get started. First of all, let's just create a diagram here. I'll be, like just say blockchain test. Name is not important. Um, so let's just create a diagram here, but let's just try to first maybe illustrate how databases or like data recording works. So initially, in a normal setup, let's say that you're texting some messages to your friends via WhatsApp or like any other instant messaging application. So when you plan on sending some message to your friends through the application, what you do is that you type some message. Like right now, I have my cell phone here. I type a message, and then that message is from me. Let's just illustrate it here. I could be this guy over here, and I'm sending a message to someone. Let's say this is my message. And then there are like the servers of WhatsApp because like my message is here, and then they're delivered to the let's just say WhatsApp servers. I mean, there are like different intermediary connections to ICPs, internet service providers. But all in all, in general, my message goes to WhatsApp servers. And then WhatsApp servers checks the recipient. And if it's a group chat, WhatsApp servers checks for the phone numbers for like the users in that group chat. And then WhatsApp servers does this. Let's say there are like different users. There are like different users. And the WhatsApp server says, like, let's just do something like, okay, maybe we can do like a box here to illustrate things better. So let's this. So this is, let's say this is Osman's message now after WhatsApp server reads it. And then it delivers the message to, the participants of that group chat. So this is basically how it happens. Now, as a person who received that message, um, you cannot verify the sender's identity, which means that this message here is being transmitted through the WhatsApp servers. So actually, from this guy's perspective, this guy has seen some message that is claimed by, that is claimed that it's Osman's message, but the information source here, which I'm going to be highlighting with green, is the WhatsApp servers, or are the WhatsApp servers. Now, WhatsApp says that they're using end-to-end encryption, which means that my message over here, let's just find the lock here. Maybe if we can. Oh, all right. Nope. So WhatsApp says here, your message is encrypted on your device, and it's transmitted to their servers, via encrypted way. Let's just do something like this. So the message is here in an encrypted way, and then when it reaches to the receiver's phone, it's being decrypted. However, we know for a fact that that encryption key is stored on the WhatsApp servers. So, um, you know, it's not, how do I say, it's not hard for WhatsApp to forge messages and claim that, it's sent by me. So this is in general how the messaging services, or like any other thing. Or right now, I'm sitting at my home and I am streaming some video, right? You're watching this video being browsed to you from the YouTube servers. In fact, actually, I am first streaming that video to YouTube, and then YouTube is, redistributing that live video to your computers. So that's in general how web services, or like Web 2 services, as people call it, work. There is a central database, or like a centralized authority here for a service provider that, provides the data to the end user. Now, the important thing here is when Satoshi first thought about a way that could be, that could work in a trustless manner. What I mean by trustless manner is that the end users should not be relying on the WhatsApp servers or any other server. Um, he thought about the blockchain technology. We'll be coming to that later on. Before Satoshi Nakamoto, there were like different cryptographers who worked on the field, but the main problem was double spending. So let's just first illustrate what is double spending here. Further understand, or like further explain the situation. So let's say there are like two people, two actors, and I'm going to be marking them, maybe I can color them, maybe I'll mark them green. So you know that they're the bank operators. And let's say this is a bank with two branches that work in a trustless way, in a distributed, decentralized way, for example. And they keep a table. They keep a balanced table that keeps how much money each user has. So it basically says Jack has, let's say, like $500, and Bill has, let's say, $300. This is the information they have in their record. Now another person comes. I'm going to be marking them with red because they're going to be the attacker. I'm not changing the names. So the attacker here comes and says that, let's just do like that. Okay. They say that I want to deposit like $100. But they deposit $100 to this bank account over here. And they say that increase my balance. Now, the first branch of the bank says that, okay, now the actor has, $100 balance. Now, this is the scenario here in the first place. Let's just copy that here to further illustrate the situation. Now, the actor here, let's just clone that one as well. On the other side, as a legal representative, which means that, let's just say here, legal representative of the actor. Basically, that means that in our scenario, this guy has the authority to withdraw money from the bank account of the actor. But before we do that, after that deposit, this bank branch calls the other bank and says that, hey, credit like 100 to actor's account, which means that, that branch of the bank, let's just do like that, should add $100 to the actor's account. So the bank becomes like, okay, he has $100 balance. Um, Here, let's just copy paste that. Let's just delete that here. Now the system isn't synchronized. So the actor deposited $100. The first branch, processed the deposit, updated their logs. Then they made a phone call to the second branch and said that please update the actor's balance. No problem there. Now the problem starts when the actor, let's just illustrate the thing here. When the actor goes to the bank and says, I wanna withdraw my $100. And let's just give it a time. For example, 6:10 p.m. right now. Just right now, we're recording the video. The actor goes to bank, says that they want to withdraw their $100. And the legal representative of the actor at the same time says the same thing to a different branch. Says, I want to withdraw the actor's $100, and it's again 6:10 p.m. Right? So both of them simultaneously, just like in the movies, go to the bank at the same time. Let's just fix that. And they say that at the exact same time, the actor goes to one branch and the actor's legal representative goes to the other branch and says that they want to withdraw, $100 from the account. Now, the first branch, of course, checks their records here. And they say that, of course, you can withdraw because you have $100 balance. And the second branch also checks the accounts and checks all the legal documents and says to the legal representative that, yes, no problem. You can withdraw the $100 because the actor has $100 balance. So this branch pays $100 to the actor because, they demanded. And the second branch, let's just, fix this thing over here. I'm going to just do that. All right. And the second branch also says that, yeah, here, sure, no problem. You can withdraw that $100 too. And both the actor and the legal representative of the actor have withdrawn $100. So at the end, the actor had deposited only $100, but because both of these parties requested to withdraw the money exactly at the same time, they both received $100. Because right now, both of them check their books and say that, okay, no problem. So now there comes the funny part. They update their books, both of them, says that the now actor has, $0 balance. And one of them calls to the other one and says that please update the actor's balance because he just withdrawn, money from me. And the other branch says, wait a minute, how can he withdraw, money from you? Because I have also just paid like $100 to their legal representative. And that's when the problem starts. That's what we call double spending. Because at that moment, just because they have asked you to withdraw the money at the exact same time, the system processed the, withdrawal twice, which caused, actor to double spend the 100 they own, and now they have $200. So they netted $100, they made a $100 profit, while the bank lost $100. So that was the problem of the, distributed systems or like a decentralized or more of a trustless systems, I could say, until blockchain technology have emerged. So the situation was exactly like here, like in the instant messaging, there was like a central relayer for those transactions and messages. But for financial transactions, if you wanted to get rid of them, you were having double spending problems. So right now we understand the double spending problem here. You know, the double spending problem here. Now Satoshi said that, if we have a double spending problem, in the case that we have, two branches, three branches, five branches, whatever we have, let's just make some, cute nodes here. Let's just some blockchain nodes. So if we have the problem of double spending, how do we solve things? How do we, solve this problem? How can we eliminate the risk of double spending? And he found the idea that instead of processing transactions exactly at the same time, simultaneously in real time, he said that let's just do that. Let's just, paint a reactor here. Let's just make something called mempool. I'll call this mempool over here. Or even better, let's just do that. Let's just say mempool here. So he invented something called mempool first. And he said the actor, if you want to send some money, let's just copy that right here. And we bring it all the way down here. He said that, or like they said that, if you want to do such transaction, your transaction goes to mempool, right? The transaction first goes to mempool, where the transactions are just waiting. Okay, so your transactions are not exactly processed simultaneously, lifetime, real time. Instead of having that, your transactions are now going through, a pool where there are a lot of different transactions. So let's just illustrate them here as well. Let's just change the colors. There are like different transactions in the mempool. Do that. All right. There are like 4 different transactions on the mempool that now wait to be included in the blockchain. But we don't know what is blockchain right now. So let's just learn about that. I'm going to move them over here. Now, Satoshi said that we need some people called miners. Let me see if we can find some here. And we have a miner here. Yep, here we have. All right. So Satoshi said that we have some people called miners who will be looking at the mempool. Let's just say they will be looking at the mempool, and they will be choosing transactions from that mempool. So the miner says there is an empty block. There is an empty block, empty page. So the miner looks at that, any miner in the world, or like any validator in the world, or from the Satoshi's product, any miner in the world, said that, okay, I want to do that. I want to do that. Those are the transactions, and I want to do that. Let's just exclude the last one. And the miner said, let's just say, let's just do here, transaction, let's do transaction fees go to me. That's what miner says. They want to, see the transaction fees. And miner includes another, I'll just change the color. So this is the miner's transaction. So miner actually builds a block. That's actually what we call a block in blockchain. So list of transactions or list of, actions, or like transactions happening in a page. You can think of it like page of a notebook. You can think of a block that contains value, that contains data. So the miner says, guys, this is my block. These are the records which I believe, because at this point, let's just copy that from here too. Let's go down. These are the nodes of the bank. All right. Let me just quickly delete that. Okay. Here. Go here. Here. So these are the nodes of the bank. All of them have the same records. And right now, um, the miner wants to update that data, in the blockchain. So miner says, "Hey guys, I have a list of transactions. There are like three transactions, and I want to keep the fees." And then miner distributes that block to every participant in the network. Maybe it's better that I split them a little bit over here. Uh, here. Let's just do that. Okay. So the miner says, "Guys, please update your, books with the new block." So let's just say here. Let's just say block 100. So the content of the block 100 here is actually all the transactions that are going to be taking place in the blockchain. So according to the 100th block, every validator, or like the node in the system, updates their database. And this thing goes on, this thing continues. But then we have the problem. So what if someone changed the contents of the block? Like what if one of the miner here, or like one of the node here, changed that data and changed the records, according to that. Then Satoshi says, "Okay, guys," and also another problem here. Transaction fees go to me. The miner says that fees go to them, but maybe there are a lot of other different miners. So how do we solve that conflict? How do we solve that problem? How do we solve the problem? Now there is one thing we can do. Let's just do that, or let's just do the better illustration. This is a nice, cool looking website. So there is something we call hashing in cryptography. So it basically means that if you say my name is Jack, whatever you have here, whatever data you have here, or whatever information you have here, this algorithm over here, this hash algorithm, takes the fingerprint of the data. Think about it like some piece of information that is specific to that data. So anytime, like let's just delete my name is Jack. Please see that, beginning of the stream, B699. So let's just delete that. Type something else. As you can see, the string changes. And as you delete it, paste it back, you'll see that the hash starts with the same string. So it's basically like a fingerprint of the human. So I'm a living human being, and I can go to some, legal authority and give my fingerprints. It'll be the same today. It'll be the same tomorrow. It'll be the next week. And it was the same a week ago or a month ago. How this works is that exactly similar to the fingerprints. Let's think about it. Let's think of a crime scene. There is some crime committed, and there are no, criminals in the area, but the investigation officers come to that area and look for, clues in fingerprints, right? Once they have found my fingerprint on the crime scene, then they take that fingerprint, go to their database, and check for, previously recorded fingerprints. One thing is that if they don't have my fingerprint in that database, there is no way that they can find me because they only have the fingerprint and they don't have any matching data. But if, or like once, I give my fingerprint sample to the system, then they can compare that fingerprint to the already existing fingerprints that they have. And if I have committed a crime or my fingerprint has been found in some crime scene, then they can say that, okay, at the crime time when the crime was committed, Osman was at that location. And then this could be the, how do I say, legally valid reason for them to arrest me because my fingerprint was there. So fingerprints are enough proof for us to, how do I say, understand and accept that that person, that exact person, or like me, I was at that crime scene. So that's one way that we use the fingerprints, right? So in cryptography, it's exactly used in the same way. So once you have the fingerprint, so you can't go back from fingerprint to the data itself. So if you don't know that, my name is Jack, it's equal to that. Just by knowing this, just like in the fingerprints, you can't go back to my name is Jack. But if you know my name is Jack means this, and then you remove that and you share that data with your friends, and 2 weeks later you claim that your secret word was my name is Jack, then you prove that you have that. So now the Satoshi's version, his solution to that problem was, let's just do two things. One of them is that, let's just go here, see a block. One of them is that, let's say transaction 1, transaction 2, transaction 3. You understand the block template. Now we have illustrated here just transactions, but there are like other things. So Satoshi's solution was each block has to have one number here. It could be like block 0, block 1, block 2, block 3, whatever the number of the block is. So in our sense, let's just say 140 block. And Satoshi said include all the transactions in the block template because this is the template of our block. And he said that, let's just make it here 0. He said that in order for a block to be valid, in order for a block to be a valid block, a miner has to, let's say, miner A receives the rewards. That. So in order for this block to be valid, Satoshi says, let's say, the hash of this, or like the fingerprint of this data over here, or the block number 140, has to be starting with 4 leading zeros. But if you look at the example, the fingerprint of that block's data not be, zeros, because it's like the fingerprints are unique to people's. It's the same, like you can't say if your fingerprint is, in some order, you can be a president, but if not, then you can't be. But what about my luck? Why can I not try again? Why can I not, find a way to find a valid block without changing data? So Satoshi said there is a number that's called nonce. It's like number only used once, or like number ones. And he said that in order to find a valid block that starts with 4 leading zeros, you can try here. Basically, that means that you can change here. You can see hash changes it because right now we're taking the fingerprint of this area, and that area. The miner starts trying that. That's what we call mining. That's actually what all those miner devices, or like proof of work miner devices do. So they put the block template here, as in this example. That's the block template. And then they start incrementing that number, randomly choosing that number to find a valid block. So I'm not going to do that manually. I'm just going to click on mine. As you can see, after trying 4,551 times for block 140, miner A found a valid block that whose fingerprint is starting with 4 leading zeros. So that's the work comes from. That's where the work of proof of work comes from. That's how mining and the work part works. So now Satoshi said that each block has to have a valid hash. Let's say starting with 4 leading zeros. It's in fact it's more than 4 leading zeros, but let's just say it's that. And mathematically speaking, the odds of finding 4 leading zeros is 16 to the power 4. So it's basically like 256 times 256. But there is again problem because let me just do that. Let's say that for block 100 we have found the valid solution. But what about block 101? And even though I keep finding valid solutions, some other miner can change that data. No, no, that's invalid. And look, can try 155,470 times while we're trying to look for other blocks and find another valid block and say that, hey, it's not the miner A's right to claim the money, it's my right to claim the money. Now, in order to solve the problem there where the chain root comes from, Satoshi said that let's just do this. Let's just find all those things. Satoshi said that this is block number one. This is, let's just say, start from 0. Satoshi said that each block specifically has to contain the hash of the previous block. What that means is that, let's just do it here. So I have, let's say, block number 1 here. They start from 0, but let's just do it here. So I have block number 1 here. Satoshi said that take the fingerprint. So here is the fingerprint of block 1. He said that take the fingerprint. Let's just do this. That. And then okay. He said that let's just do put the fingerprint of 1 at the beginning of the block or at the end of the block. Beginning of the block. Add the contents of the second block. Now take the fingerprint of the block number 2, including the fingerprint of the block number 1. That's now is the fingerprint of the block number 2. Both of these things. So if you change anything on the block number 1, if you change anything on the block number 1, it's going to be changing the fingerprint of the block 1, the first block. And because the first block's fingerprint has changed, the fingerprint of the second block is going to change too. And if it changes, let's just add it here. The fingerprint, now there is 2, that's block number 3. Let's just fix that. And the fingerprint of the block number 3 is also going to change. This way we have the we have the ability to not change or like keep the records constant and have them have immutable blocks. So let's just illustrate it here in a more understandable way. Because this is the first block or the genesis block, initially generally usually it starts with the block 0, but in our case let's just say it's the block number 1. We have the data for the first block, the genesis block, and the previous hash area, because there is no previous block. It's just zeros. And we start mining, and you see that once we have tried for 2,442 times, we have found a valid hash that is the fingerprint. Now if you see it, let's say transaction 4, 5, 6, there are different transactions, and miner A receives the reward. This is going to be miner A. So now we're at the second block. Now as we're calculating the fingerprint, we have that information here, and we have the previous block's fingerprint here too, previous hash, and we start mining. Now we have tried 67,000 times and found the second block. Now we go to the third block. Let's just do the third block. 6, 7, 8, and 9. That's it. Now let's say miner C, and then we again mine. So if you can see, we have for the valid block. Now in order to calculate this hash here, we have used this one. We have used the information here. We have used the information here, and we have used the block number. Now if you go back and try to change anything from the first block, look what happens. Let's just do this in order to further see. All right. Sorry about that. let's just see what happens. So block number one, if I change the block number, make it 0, as you can see, the hash of the block has changed. Because the hash of the first block has changed, now the second block's previous hash block, previous block's hash area also changed. And because that changed, that hash has also changed because this was calculated using data from here, 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 here. Because that changed, eventually that also changed here. And that led to change on that hash as well, third block's hash as well. So that's why in blockchain, as you see, if I change from the block number from 0 to 1, everything goes back to normal. So that's where the name chain comes from, because every block and their fingerprint is embedded into the next block. And with every ongoing block that is being added to the blockchain, let's just do that, it becomes harder and harder to reverse the transaction. Why would you would ask why? Because if the network is block height 3, now in order for me to have a valid block here, I have to first go to that block, calculate a valid hash with my own transactions, and then I have to calculate the second block, and then I have to come back to calculate the third block. But while I am doing that, the network would already be calculating the fifth block. So that's why people call 51% attack, because if you control 51% of the network's hash rate, then you have the chance to calculate blocks faster than the other part of the network. So as they're calculating, let's say one block every 10 minutes, maybe you'll have the chance to calculate one block every 9 minutes. Then you'll go faster than them so that you can change the blocks, change the previous blocks, and then catch up with the network. I mean, actually, it's not how that works, but for the sake of our, DevLogs, let's just say that it's. So at that point, Satoshi, his version of blockchain now has all the blocks connected to each other so that none of the previous blocks can change, which eventually solve the problems of synchronization errors between nodes. Because now once this block is validated, the nodes update their records according to that. And even if at some part a user says that they want to deposit something and the legal representative of them says something, no such two conflicting transactions can be included in one block. So only one of them will be included, and once only one of them is included, then the network will process only one of those transactions, and the other transaction won't happen. So this solves the blockchain technology here by calculating the fingerprints of the actual blocks. Okay, so first thing is that by not processing transactions in real time, that's one thing. You can't process transactions in real time, because once you process transactions in real time, this is what happens. So you have to process transactions, or like push them into some mempool pool of transactions, and then you have to craft a block template, and then you have to process that block template. So this is the one solution. And in order for miners or the participants of the network to have a mutual agreement on the blocks, he came up with the idea that those blocks be chained to each other. So that's where the name blockchain comes from. And if you want to learn more about how proof of work blockchain works, I would highly recommend that website. And there's Brownworth's website. If you Google blockchain demo, then you can reach that website and watch the videos, and go try distributed versions, go try tokens, and then do all sorts of fancy things here. I'm not gonna go into too much details here. So now we understand the very first reason why blockchain exists, because users don't want to be trusting on the WhatsApp servers. And we understand why blockchains cannot process transactions in real time. In fact, if we go to the etherscan.io. Let's just do it. If we go to view pending transactions area, this is the block explorer for Ethereum. I didn't go to the Omchain's block explorer because luckily we don't have any pending transactions. The blockchain infrastructure is too fast. Um, as you can see here, there are 150,261 pending transactions in the mempool, and your last seen is like 1 second ago. Those are the transactions that are not validated, or they're not included in a block right now. They're waiting to be included in a block. So let's say this transaction has been waiting for and go. See, it has been waiting for 4 minutes, 5 minutes to be included in a block. So it means that this transaction is not being executed yet. And one thing is that, they have to be included in the block to be valid transactions. Sorry about that. I feel like I'm sneeze. Okay, calm down. Now the second part is because right now we're trying to build a distributed system. So let's just go here. Please, let's just go to Ethereum. So as you can see, there are like 8,758 different nodes or like servers, like different computers in the world. They're keeping that table, they're keeping that information, and they are keeping the state, they're keeping that table. Who has how much data, how much money, whatever. So now the problem comes to block size. Because eventually think about it, like, okay, you're putting all the transactions in some mempool and they're stored, waiting to be included in the block. But every few minutes or few seconds or every certain minutes or seconds, you can broadcast, some, how do I say, specific amount of transactions to the other participants of the network so that the network can keep up. Like, think about it. If I have to every time call my friends, let's say I'm in a class with 19 other classmates, so in total we're 20 students. If for everything that our teacher says, I have to call 19 of my friends and they also have to call each other, then I'll have to make 19 calls every time my teacher says something. So I can't call them every time because then, we would have conflicts and we couldn't, synchronize. We wouldn't be able to synchronize. So what I do instead is that I go to class, take my notes for 1 hour, then I call all my friends, so all of us call each other, and then we settle on something. And the next hour, we also do the same. So that's why we have average block time here. If we can go here, um, maybe short statistics. Nope. Maybe in gas tracker, I believe. Nope. Where was it? Average block time, latest blocks. Nope, we don't have it. Maybe in the blocks. Nope. All right, so you can here see Ethereum. They're like 15 seconds. I'll just here statistics. Nope. Actions. Oh, okay, maybe in charts then. In charts there is, but I don't want to average block time chart. Let's go here. I'll just focus on here. If you can see on Ethereum, every 12 seconds there is a new block that is being generated by some validators right now, and that is included in the blockchain. It takes 12 seconds for a transaction get involved in a block, get included in a block. So that's the limitation of the blockchain technology, because instead of doing it real time, so that's why when people talk about blockchain-based solutions, like I want to store a file on blockchain, they actually don't store the file on blockchain. They just store the hash of the file or some metadata related to that file that can't be changed. And it costs a lot of money to store or like broadcast transactions on the blockchain, because there is only a limited amount of space for a block, for a certain block in the blockchain, because you can't also transfer like 200 megabytes of data every 12 seconds to the other nodes in the network, because maybe some of the nodes can't keep up, some of the nodes will be, left out, some of the nodes don't have that good internet connection. And that's actually what happens to Solana, because once there's some, you know, people trying to DDoS the network, that means they're broadcasting a lot of different transactions to different nodes. The system cannot, be synchronized so that the network halts. That means that the block producing the block the process of producing blocks stops. So this is in fact how the proof of work Satoshi's version of the blockchain technology works. So now if we go back to over here, we understood what was the problem. People don't want to trust the WhatsApp, and we understand that blocks could be generated in a distributed way. Now the question is, we understand proof of work. It's where you do the work, you register a new block, you get the reward, and so on. Now proof of stake says that whoever has the most money, or like um, relative to the proportion of the you know tokens or coins stake, let's just find a way that is fair to everyone, and distribute sorry give the block generation right to participant, or like stakers in the network, proportional to their staked amount. So the system says that instead of having miners here, let's just delete them. um, it says that first you generate the block, next you generate the block, next you generate the block, and so on, depending on the amount of tokens that they have staked. Um, However, if we technically technically look at it, the main problem was the double spending, right? We don't want things to be double spent. And the second problem is that this system provides immutable data storage, which means that if some data is being recorded into the blockchain, it can't be changed. But it can't be changed only if it's a proof of work network, some miner has to go back, do all the hard work, change the data, come catch up with the network. So if it's a proof of work network, there is no way for any attack vector in the world to change that data without doing the work. So that's why even if someone right now forks the blockchain of the Bitcoin blockchain, they can't change any past data without making some changes in the code of the Bitcoin core. So proof of work is the most secure consensus algorithm in the world, mathematically proven security. Next, there comes the proof of stake. But proof of stake does not rely on mathematics. Instead, it relies on the amount of nodes, participating in the network. Because it's basically a way of saying that, hey guys, we're like 8,000 people, all scattered around the world, and we all keep, you know, we all keep records of the transactions happening on the blockchain, and we all agree that we're not going to change that data. So on the off chances of that 8,000 nodes are being controlled by only one person, there is a chance that they can alter the blockchain if there are no other peers, people who are watching that blockchain. So proof of stake blockchains rely on the participants included in the network. There are like 8,000 validators. There are like 80,000 validators. That's even better. Um, but on the other hand, if we think about it, the problem of block limit and the block interval emerges from synchronization issues, because there are like 8,000 different people who has to be notified of every block in order to be able to participate in the block generation event. So they all have to know about every specific block that is being generated every 12 seconds. That limits the block size and the performance of the blockchain infrastructure. Now, our solution in Omchain is that let me tell you how Omchain and our vision actually is. So here in Omchain, we say that, let's say OMC. All right. So here in Omchain, we have, even the number does not matter, but that's 4 and that's 7. So we have 7 different validator nodes that are all operated by us. We say that we're providing you the infrastructure that is reliable, because even if one of them, like if this one fails, there are still 6 nodes that you can connect and interact with. So if 2 of them fails, no problem. 3 of them fails, no problem. You can still continue using the blockchain, and even if that one fails, no problem. You can still keep using the blockchain. Nothing changes. You can still access the blockchain. You can still access the data. But because we control all the nodes in the network, there is nothing stopping us actually from going back, changing the contents of the block, and then moving on with the new blocks. But one thing here, our vision is to provide blockchain infrastructure that is needed by you know companies and businesses and developers. So one thing a company can do here is that I'm going to be marking those validators here in blue. Let's say we have a company A here who is using the Omchain's blockchain infrastructure here, and who is deploying their smart contracts, solutions, products, and whatever. They can run a peer node, which means that this is actively watching over the network. It's not being part of the block generation, but it synchronizes with the network, and it keeps checking and it keeps asking, like, give me the new records, give me the new records. What happened next? I want to know. I want to know. And keeps the local, you know, copy, keeps the, copy of the blockchain in their local storage. So if, as a company, as the service provider here, we change the contents of the blocks or blockchain, that company A can detect that change. And if we don't change anything, if everything goes all right, then there is no problem, because there is no trust issues in the company and the blockchain industry. So if they just, watch the transactions, it's enough for them to know that, the system is secure and the system is operating functionally. And because there are 7 nodes that actually generate blocks, they can be, interacting with each other in a faster pace, and they can process much more transactions than any other blockchain. Um, and if there is another company B, that wants to check all the blocks being generated, they can go and ask another node in the network, another validator node in the network, or any other peer node, but then they would have to trust the peer node. So any other node in the network, validator node, they can go and query them and ask for transactions from them. This way, we actually provide the way to companies to make sure that our blockchain infrastructure is secure. And we also tell them, look, listen, you don't have to store all the data here as well, because let's say a company starts storing the data for our blockchain from the first day of the, or like from the Genesis block. For 1 year, they observe the blockchain, see that everything is right, they audit, everything is checking out. They can delete all that data, and they can start recording the upcoming blocks. So they can only keep the last 1 month, they can only keep the last 2 months of the blockchain to make sure that everything is going all right. Because we're living in a world where trust is based on the, how do I say, companies, people, products. And in the case of Ethereum too, even though there are like 8,000 different nodes, or more than 8,000 different nodes, the products and tokens, if we can go over here, number one token is USDT. So if the company behind the USDT, just like the UST, Terra Luna, if the company behind the USDT goes bankrupt, then there is no added value or added profit of the USDT to the token holders, or like the Ethereum network users, or USDC, or BNB, or Binance USD, or even Shiba Inu. If the team behind it, if the community behind it disappears, then there is no added value of the blockchain at 8,000 different nodes. So here our problem was simple. Our problem was to have a trustless way that we wouldn't trust the WhatsApp servers because we don't know what they say. Instead, we here provide companies that you don't have to trust us because each transaction is signed by the user. Each transaction is signed by the, you know, sender. So unlike WhatsApp, we don't store your private keys. Your private keys belong to you. So we can't forge a transaction. One thing we can do is that we can block the transactions being included to the blockchain, but right now it's the problem of Ethereum too. And we believe that in a fair world, in a just world, if there is some criminal activity or some illegal things going on, then we should be working closely with the law enforcements to provide this stable infrastructure for companies to operate, because that's the nature of the world, and that's the nature of uh, how do I say, our blockchain infrastructure. So for that reason, we believe in a world where people use the blockchain technology in a way that is beneficial to them. We don't use blockchain technology with excess words like decentralized, decentralization, tokenization, all sorts of things. We mainly focus on the technology, and we provide the companies a trustable infrastructure that they can, use, and they'll make sure that if there's some, problem, illegal activity and something, that is going to be dealt with. Because if it's not going to be dealt with, then it's going to be the company's responsibility to deal with that problem. So we believe in a world that our blockchain infrastructure could be much more useful to companies because it can process larger transactions. And we believe in a world that this technology is mainly used for its advantages rather than some marketing campaigns, or rather than selling dreams to people. Um, it's already been like 57 minutes. I'll be ending my words here at the second episode of the devlog. And on the third episode, I hope that we'll have the chance to talk more about how smart contracts work, and how can you, deploy smart contracts on the Omchain. And you guys can see that how easy it is to deploy smart contracts on the Omchain. So until the next episode, I wish you all a good day or good evening, and I wish you all have a again good day. See ya. Take care.